Okay, in this video lesson I'm going to discuss the concept of continuity. When you study continuous functions in your pre-calc course, you're told that a function is continuous if its graph doesn't have any holes in it or breaks in it, or if you can draw the graph without picking your pencil up off of the paper, then the function is continuous. In this calculus course, we can give a more mathematical definition of what it means for a function to be continuous using limits. So let's first take a look at what it means for a function to be continuous at a point. So suppose that f is defined on an open interval that contains x equals c. We say f is continuous at x equals c if the limit of f as x approaches c is equal to f of c. Now, if the limit doesn't exist, or if it exists but is not equal to f of c, we say that f has a discontinuity at x equals c. So there are three things that have to happen in order for a function to be continuous at a point. Three conditions that need to be met. Let me just sort of summarize this. F is continuous at x equals c if, first off, the function has to be defined there. So f of c is defined. Next, the limit has to exist there. And then thirdly, that limit needs to equal the function value. If any of these conditions is not satisfied, then f is not continuous at that point, or we say that f has a discontinuity at x equals c. So let's take a look at some different types of discontinuities. Let me put this graph up here. Here's our c, here comes my function. Open circle there, let's call this L. Now this function here, we'll call it f. Right? Note first that the graph has a hole in it right here, so the function's not continuous. It has a discontinuity at x equals c. Why? Because, well, condition number one is not met. The function's not defined there. The limits exist. The left-hand limit, as I approach c from the left, the function values look like they're getting closer and closer and closer to this value L. And the same is true if I approach c from the right. So the limit exists, but the function's not defined at c, so there's a discontinuity at x equals c. So here, let me redefine the function now at c. The function's still not continuous at c. There's still this discontinuity at x equals c. Why? Well, the function is defined at c now. F of c is equal to m. The limit still exists, but the limit is not equal to the function value there. Note that I wouldn't be able to draw this graph without picking up the chalk off the chalkboard up here. We say limits of this type or discontinuities of this type are said to be removable. F has a removable discontinuity at x equals c if the limit exists but either f of c is undefined, like it was in the first graph, or the limit doesn't equal the function value. And this is called a removable discontinuity. We call it a removable discontinuity because we could remove the discontinuity if we redefine the function to be equal to the limit, right? If instead of having the function defined at c to be equal to m, if I just said, okay, now I'm redefining it, now the discontinuity is gone, we've removed it. So this is one type of discontinuity that we could run across. Let's take a look at some others. Put up this graph. C, okay, call that L, and this, call that M. Right. And note the graph has a break in it, so I know the function's not continuous. The reason it's not continuous, well, the left-hand limit looks like it's equal to L. The right-hand limit, as I approach C from the right, the function values are getting closer and closer to M. So the left-hand limit is equal to L. The right-hand limit is equal to M. So this two-sided limit does not exist. So the function has a discontinuity at x equals C. We call discontinuity that looks like this a jump discontinuity. F has a jump discontinuity at x equals C if the left-hand limit and the right-hand limit both exist but are not equal. So if the one-sided limits exist, but are not equal, we call these jump discontinuities. While I have this picture up here, I can use it to talk about a function being left continuous at a point or right continuous at a point. So this function here is left continuous at x equals c. F is left continuous at x equals c if the limit as x approaches c from the left is equal to the function value there. Right, we still have this jump discontinuity at x equals c. The function's not continuous at x equals c, but it's left continuous at x equals c. The left-hand limit is equal to L. The function value is equal to L. So in the same way we could talk about right continuous. Right? Let me change the graph so that the function still has this jump discontinuity, but is right continuous at x equals c. So it would look like this. So f is right continuous at x equals c if the limit as x approaches c from the right is equal to the function value. All right, well, there's one other type of discontinuity I want to look at. And to do it, let's do this. Let's look at this function. Right? this rational function. Let's graph it. This is something that we all are taught how to do in our pre-calc course. The graph of this function would look like this. It has that vertical asymptote at x equal 2, right? The function's not defined at x equal 2. Right? 2's not in the domain of this function. So I'd have that vertical asymptote at x equal 2. My y-intercept would be down here at -1/2. The horizontal asymptote would be the line y equals 0. The graph would look like this. So we have a discontinuity at x equal 2. Well, this condition isn't satisfied. This condition is not satisfied. This condition is not. It fails all three of those conditions, right? We say this type of discontinuity is an infinite discontinuity. F has an infinite discontinuity at x equals c if one or both of the one-sided limits is either plus or minus infinity, right? F has an infinite discontinuity at x equals c if one or both one-sided limits equals plus or minus infinity. Okay, so this function has an infinite discontinuity at x equal 2. All right. One more thing I want to talk about before I pause the video and give the second part of this lecture is what does it mean for a function to be continuous on an interval? Right? The definition that we started with talked about what it means for a function to be continuous at a point. Right? And there are the three conditions that have to be satisfied in order for a function to be continuous at a point. So let's do this. Let I be an interval of the form, one of these, open interval, closed interval, half open interval, this one. Okay. So we've got some interval that looks like one of these, then f is continuous on the interval if f is continuous at each point in this interval. F is continuous, F is right continuous at x equal a if a is in the interval. And if f is left continuous at x equal b if b is in the interval. So what it's saying, to be continuous on an interval, you've got to be continuous at every point it's in that interval. Now, if we're talking about the endpoints, you're either going to be left continuous or right continuous there. Okay, let me shut down the video here and prepare the next one.